All right, so we are here doing sets 11, 12, 13, and 14. I'm so sorry for just now posting a video on this. I have been very ill, which is why my camera's not on. Nobody wants to look at me right now. But I do want to, these are really important concepts, using laws of motion with conservation principles. Super important. So I wanted to make sure that I did have some kind of commentary, some kind of video. I'm going to go through this fairly quickly. I'm not going to do what I usually do, where I solve the problems with you. I'm going to just go through the problems that I've already solved that are posted online, kind of explain what I've done, why I've done what I've done. And then if anybody has any questions, please reach out. I can solve a problem with you if that's necessary and explain a little further. All right, so let's get to it. Our first problem, number 9. Yeah. Sorry, I have to authenticate myself in order to open the book. So we are in chapter 5. Our first problem is number 9. I apologize for the loud noises here. 2 of my cats have decided they want to be very noisy. All right, so number 9. Mechanic pushes a 2.50 times 10 to the 3 kilogram car from rest to a speed of V, doing 5.00 times 10 to the 3rd joules of work in the process. During this time, the car moves 25.0 meters. Neglecting friction between car and road, find V. And the horizontal force exerted on the car. Okay, so we are using kinetic energy and the work energy theorem. So like always, we're going to start our problem writing what we're looking for, and that is VF, our final velocity. And we're going to write what we know. So we know that initial velocity is 0. So VI is 0. We know mass of the car. We know the work that's done, and we know delta X. So let's write down the equations we know. We know that work equals the change in kinetic energy, and we know that kinetic energy equals 1/2 mv squared. So using work equals delta KE equals equals final kinetic energy minus initial kinetic energy. So we've done that here. We know that the initial velocity is 0, so we can take that to 0. So we end up with V squared equals W over 1.25 times 10 to the 3rd kilograms. We do some canceling. We put in work that we were given, 5.00 times 10 to the 3rd, and we end up with 4.00 meters squared second squared, but that's velocity squared, not velocity. So we're going to take the square root of both sides, and we're going to come up with the ending velocity of 2.00 meters per second. And now we want to know the horizontal force exerted on the car. So again, we write down what we're looking for. We're looking for the horizontal force. We already have all of the knowns written up on top. We are going to write down equations that we know, and we know that work equals force times the distance the car traveled. So W equals F delta X. We rearrange the equation so that we're solving for the horizontal force. We plug in what we're given, 5.00 times 10 to the 3rd joules divided by delta X, which is 25.0, and we end up with 200 newtons. Putting that in significant digits, we have 2.00 times 10 to the squared newtons. All right, fun problem. 16, moving along. 16 says a 0.60 kilogram particle has a speed of, excuse me, 2.0 meters per second at a point A and a kinetic energy of 7.5 joules at point B. What is its kinetic energy at A, its speed at B, the total work done on the particle as it moves from A to B? All right, so once again, we're starting with what do we need? What do we know? So drawing a little diagram here, which didn't really help us for this one, but I did it anyway. Write down what we need. We need kinetic energy at A. Write down our knowns. Our knowns are V equals 2.0 m over s, and 0.60 kilograms is our mass. We know that kinetic energy is 1/2 mv squared. Plugging in what we're given, we end up with 1.2 joules. B says its speed at point B, so we're looking for VB. We know that kinetic energy is 1/2 mv/b squared. Plugging in what we're given here, rearranging to solve for V, and we end up with VB squared equals 25 meters squared over second squared. Taking the square root, we get 5.0 meters per second. The total work done on the particle as it moves from A to B. So we know that the work done equals the force times the distance, and that equals the change in kinetic energy. So we have been given kinetic energy for point B. We solved for kinetic energy for point A. So we're just going to take the final kinetic energy minus the initial kinetic energy, 75 or 7.5 joules minus 1.5 joules, and we end up with 6.3 joules. All right, 25. I drew a pretty fancy picture here in this one. I'm proud of myself of that. Okay. A daredevil on a motorcycle leaves the end of a ramp with a speed of 35.0 meters per second, as in the figure I've drawn. If his speed is 33.0 meters per second when he reaches the peak of his path, what is the maximum height that he reaches? Ignore friction and air resistance. Okay, so once again, I've drawn a little fancy diagram here. We are going to write what we need, write what we know. So we need to know H, let's call it. So we need to know this. We are given initial velocity, which is 35.0 meters per second. We are given final velocity of 33.0 meters per second. We are ignoring friction and air resistance, which means that all forces are conservative. So we can say that initial energy equals final energy, or energy equals kinetic energy plus potential energy. So initial kinetic energy plus initial potential energy equals final kinetic energy plus, that should be a plus, not equals, plus final potential energy. So we're going to plug in the values that we know. We know that at the end of the ramp, there is no potential energy because our daredevil is on the ground. So we can cancel off initial potential energy. We can cancel off our masses because the mass of the motorcyclist doesn't change. And we enter in our knowns, do a little algebra, and we end up with 6.9388. Using significant digits, we end up with H equals 6.94 meters. All right, so still in chapter 5, we're going to 37. It says 37A or B. I am the TA, which means for me it is 37A and B. So I have done both here. I tried to draw Tarzan, but he came out just looking like a dot with a string. I tried. Tarzan swings on a 30.0 meter long vine, initially inclined at an angle of 37.0 with the vertical. What is his speed at the bottom of the swing if he starts from rest? If he pushes off with a speed of 4.0 meters per second. Again, we are assuming that we are neglecting air resistance. because it wasn't given. So that means that all of our forces are conservative. We are looking for his final velocity. And A, we are given his initial velocity is 0. So we've got theta is 37.0 degrees. And we have L, which is the length of the vine, is 30.0 meters. So again, we're just looking at the force of gravity here, and that is going to be energy initial equals energy final. Again, we've got the same, got our same equation. We are going to cancel off initial kinetic energy because it says he starts from rest. And final potential energy, because at the bottom of the swing, he is at his lowest, and so there is no gravity. And we end up with a few unknowns here, not enough equations to solve. So what we can solve for is H. So H is going to be this right here. So take this minus this. We didn't do a great job of, because that should be up here. This minus this, that's H. So let's solve for H. We again are going to use our cosine bar SOHCAHTOA. And here we are using cosine theta equals L minus H, because that is going to be our adjacent over L, because L is our hypotenuse. Rearranging and plugging in what we're given, we get H equals L times 1 minus cosine of 37. We're going to plug that into this equation and solve for V. So what we end up getting is VF squared equals 2 times G times 30 times 1 minus cosine 37. We get 118.40556. Take the square root because that is velocity squared. And we end up with 10.9 meters per second. All right, so now we're going to be having an initial kinetic energy. So before he starts at rest, just lets gravity pull him down. Now he's going to kick off on something and give himself a VI. So we're going to change VI from 0 to VI equals 4.00 meters per second. We're going to do very similarly what we did before. All we're going to change is initial kinetic energy isn't going to cancel out. So mass is still going to cancel out because Tarzan is not losing weight or gaining weight as he's going along. Here you can see crossed off M. I am entering in here all of the knowns, and we end up with VF squared equals 2 times 8 plus 294 times 1 minus cosine of 37. Plugging it into your calculator, you get 134.384. Taking the square root of that, we get final velocity is 11.6 if he gives himself a push off of 4 meters squared. All right, moving on to set 12. We are still in chapter 5. We are going to head to problem 45. All right, drawing a little picture here again. Kind of difficult to see. 45. A 2.1 times 10 to the 3 kilogram car starts from rest at the top of a 5.0 meter long driveway that is inclined at 20%, or sorry, 20 degrees with the horizontal. If an average friction force of 4.0 times 10 to the 3 newtons impedes the motion, find the speed of the car at the bottom of the driveway. Okay, that's a lot. So we're going to start up with what we need. And what we need is final speed. We are given the car starts from rest, so we have initial velocity 0. We are going to make our little triangle again like we did up above. And here we are looking for Here we are looking at the opposite side instead of the adjacent side of our angle, and we end up with H equals L sine of theta. We're given L 5.0 meters, we're given theta 20.0, and we're given what the friction force is, and that is 4.0 times 10 to the 3 newtons. So writing down the equations that we know that work equals force times the change in X. And we also know that the work of the conservative forces plus the work of the non-conservative forces, so friction in this case, wind resistance, air resistance, that would also be a non-conservative force, is going to be our change in kinetic energy. So work equals F delta X. F is going to be Fg minus F, force of gravity, minus force of friction, times L. L is our delta X. We're going to plug in what we know. So here we're going to use this little diagram that I've drawn to come up with friction force is mg sine theta minus force of friction times L equals the change in kinetic energy, which is kF minus ki, 1/2 m vf squared minus 1/2 m vi squared. Vi is 0, so that goes away. Plugging in what we know, we get 2L, m we know, g we know, theta we know, friction force we know. We got 2 times 5 times 2100 times 9.8 times 920 minus 4000 divided by 21,000, and we get 3.7966 if you take the square root of it. This one I did a little differently. Usually I write it before and then take the square root, but I guess this time I just was skipping steps. Using our proper placement of decimal, we have 3.8 meters per second for our final velocity. All right. 67. I have to change page for that. I sure do. A couple pages. A 75 kilogram imp steps out a window. This one is terrible. This problem is terrible. I couldn't even believe it. I actually read it out loud to my future husband and was like, oh my gosh, listen to this problem. All right. A 75 kilogram imp steps out a window and falls from rest a distance of 1.0 meters to a sidewalk. What is his speed just before his feet strike the pavement? Ouch. So we're going to write what we need. We need his final velocity. We know his initial velocity is 0. We know that his delta x is 1.0 meters. This we're just going to plug into our, we can just plug into our old kinetic equations that we already know. Vf squared equals vi squared plus 2ax. And we end up with Vf equals 4.4 meters per second. All right, so B, we're gonna have to step it up a little bit. We're gonna have to use some other equations that we know. B says if the man falls with his knees and ankles locked, the only cushion of his fall is an approximate 0.50 centimeters given the pads of his feet. Calculate the average force exerted on him by the ground during his 0.50 centimeters of travel. This average force is sufficient to cause damage to cartilage in the joints or to break his bones. I think that professor is messing with us on this problem. I think he had to have just laughed at this problem. That's why he gave it to us. All right, so here we need to know what the force is when he hits the ground. And we know that the delta X is going to be 0.50 centimeters. Again, we're assuming all conservative forces, neglecting air resistance and friction or whatever. We know that work equals the change in kinetic energy, and we know that final kinetic energy plus initial kinetic energy equals final kinetic energy plus final potential energy. I kind of rearranged it. So I'm having problems spitting it out. His final is going to be 0 because he is, hitting the ground. So we can say that work equals negative initial kinetic energy minus his potential kinetic energy. And we also know that work equals force delta X. So we're going to say F delta X equals negative KEI minus PEI. We're going to plug in all that we know, and we end up with 145935 using our correct placement of our decimal. We're going to have force equals 1.5 times 10 to the 5 newtons. That is a substantial force, this poor guy. All right, so we're going to backtrack and go to 65. An archer pulls her bowstring back 0.400 meters by exerting a force that increases uniformly from 0 to 230 N. What is the equivalent spring constant of the bow? All right, so again, what do we need? We need K. We are given initial force of 0. We're going to assume that she is starting at a neutral position. She is going to pull it back, and final force is going to be 230 N. We know delta X is 0.400 meters. And we know that F equals negative K delta X. We are going to rearrange for K, and we're going to get 575 Newton per meters. All right, B. Screen's going to jump here, sorry. B, how much work does the archer do in pulling the bow back? Well, we know that work equals F delta X. We know that work equals change in energy. So VI equals 0, VF equals 0. We can say that work equals the change in potential energy. We know that potential energy of our bow is going to be 1/2 kx squared. Delta PE is going to be 1/2 k delta x. Initial x is going to be 0. We're going to plug in what we know. 1/2 times 575 that we solved for up here times 0.4 squared, and we get 46.0 joules. 74. This one I had to think about. Oh, that's the end of this. Okay. All right, 74. 50.0 kilogram student evaluates a weight loss program by calculating the number of times she would need to climb a 12.0 meter high flight of steps in order to lose 1 pound of fat. Metabolizing 1 kilogram of fat releases 3.77 times 10 to the 7 joules of chemical energy, and the body can convert about 20% of that into mechanical energy. The rest goes into internal energy. A, how much mechanical energy can the body produce from 0.50 kilograms of fat? Okay, so let's start off with what we need. How much mechanical energy do we need? And our given initial mass is going to be 50.0 kilograms. Final mass is going to be 49.6 kilograms. And we know that our height of our stairs is going to be 12.0 meters. So we know that the change in chemical energy is for 0.45 kilograms of fat is going to be, Our change of chemical energy for 1 kilogram of fat is going to be 3.77 times 10 to the 7 joules. They've given us that. And for 0.4 kilograms of fat, it's just going to be 3.77 times 10 to the 7 times 0.45. And we know that mechanical energy that we're looking for is going to be 20% of the change in chemical energy. So let's plug in what we know. 0.2 times 3.7 times 10 to the 7 joules times 0.45, and we get 3393000. Wait, 3393000, only 3 zeros. Mechanical energy is going to be 3.39 times 10 to the 6 joules. All right, B. How many trips up the flight of stairs are required for the student to lose 0.45 kilograms of fat? Ignore the relatively small amount of energy required to return down the stairs. So we're only looking at when she's going up the stairs. So we're not going to multiply it by 2. We're going to just look as she's climbing. So mechanical energy is going to equal potential energy, and our potential energy is mgh. Our mechanical energy is mgh, plugging in what we know. We've got 50 kilograms times g times height of our stairs, and we get 5880. So that is our mechanical energy for 1 flight of the stairs. Let's find the number of flights of stairs. So we're going to look at mechanical energy needed divided by the mechanical energy that we are expending for 1 flight of stairs. And we end up with 3393000 divided by 5880, and we get 577.0408, or she needs to make 577 trips up the staircase. Whew, that is a workout. All right, so that concludes our set 11 and 12. Let me get over to set 13 and 14. Ooh, our first one here is a fun one. I can get up to it. So still in chapter 5, we're going to look at problem 69. I think I have to, no, I don't. Okay, problem 69. 2 objects, mass 1, 5 kilograms, mass 2, 3 kilograms, are connected by a light string passing over a light frictionless pulley. The 5 kilogram object is released from rest at a point H above the table. Determine the speed of each object when the 2 pass each other. All right, so let's draw a little diagram. We don't know what the final velocity is. We know that the initial velocity of both is 0. We know the masses are 5 and 3 kilograms. We know that the height of mass 1 is 0. We know the height of mass 2 is 0. We know the height of mass 1 is 4. When they pass each other, their heights are going to be equal. We also know we're assuming that they're going to be moving at the same velocity, that they're not going to be, mass 2, for instance, is going to jerk straight up, that they're going to move together. We will see later in the problem that when mass 1 hits the ground or the table, mass 2 continues to go, and we're going to do some calculations with that. So again, we only have conservative forces at play here, just gravity. So we know that initial energy equals final energy, which again is our little Ke plus PEI equals KEF plus PEF. Also, we know that the kinetic energy, so we can turn that into this using this entire system. So KE1 plus KE2 initial plus PE1 plus PE2 initial is going to equal KE1 plus KE2 final plus PE1 plus PE2 final. Velocities are the same. We know that H is halfway between them. So plugging in what we know to this equation here, lots of stuff is going to cancel out because both of them aren't moving initially. And we end up with mass 1 times G times the initial height equals 1/2. Both of the masses together, because we're looking at the system, BF squared plus G, the end height, times N1, M1 plus M2. plugging in what we know, lots of numbers, solving for VF squared, we end up with 3.13049. Final velocity is 3.13 meters per second. Okay, determine the speed of each object at the moment the 5 kilogram object hits the table. So again, we're going to use our conservation laws. Initial kinetic energy equals, or initial energy equals final energy. We're going to plug in what we know here. And we're going to end up with B squared equals 2GH M1 minus M2 over M1 plus M2. Square root is going to give us 4.4271. So the velocity when the 5 kilogram hits the table is 4.43 meters per second. Now we're going to figure out how much higher the 3 kilogram objects will travel after the 5 kilogram object hits the table. This is a little different question. I like this question. Makes you think. All right, so again, we're going to use conservative forces. We are going to cross a lot of stuff off again. One of the great things about this problem is that at a lot of times, velocity is 0. And so velocity is 0 and H is 0. So we can cross lots of stuff off, which I've done here. Lots of things go to 0. After we've crossed off what goes to 0, we end up with 1/2 M2 VI squared plus M2 GHI equals M2 GHF, and HF is what we are solving for. We're going to plug in what we know, what we're given, what we solve for above, and we end up with HF equals 0.9505 or H equals 1 meter. It travels 1 meter, keeps going after the big box hits the table. All right, our last problem in chapter 5 is 55. We're going backwards here. Let's turn the page twice. All right, under normal conditions, the human heart converts about 13.0 joules of chemical energy per second into 1.3 watts of mechanical power as it pumps blood through the body. A, determine the number of calories required to power the heart for 1 day, given that 1 calorie equals 4,186 joules. Okay. So we know that power equals work over delta T. We know that work equals force times distance divided by the change in time. And we also know that work equals change in kinetic energy. We're looking for number of calories. So for the first one, we have to change our units because they don't match what we're looking for here. We're looking for joules per day and we're given joules per second. So we're going to take 60 seconds over 1 minute times 60 minutes over 1 hour times 24 hours over 1 day. You could certainly do 36,000 seconds per hour. I wrote everything out. And you end up with 1,123,200 joules per day. We are going to change that into calories, and we know that 1 calorie equals 4,186 joules. So we are going to divide 1,123,200 by 1,4186, and we get 268.323 or 268 calories per day. B asks, metabolizing 1 kilogram of fat can release 9 times 10 to the 3 calories of energy. What mass of metabolized fat would power the heart for 1 day? All right, so we are going to take what we solved for above, which was the 268 calories per day. We are going to convert that into kilograms per day. We know that 1 kilogram over 9.00 times 10 to the 3 calories is going to give us that. So we put in what we know, do a little math, we come up with 0.029814 or 0.0298 kilograms or 2.98 times 10 to the negative 2 kilograms per day. All right, moving into chapter 6. We're moving out of energy and into momentum, impulse, and collisions. Ooh, our problems are going to start to get fun. All right. Oops. Number 2. You know, this one's got to be a quick problem because it's one of the first problems. Number 2 says a high-speed photograph of a club hitting a golf ball shown in this figure. The club was in contact with the ball initially at rest for 0.0020 seconds. If the ball has a mass of 55 grams and leaves the head of the club with a speed of 2.0 times 10 to the 2 feet per second, find the average force exerted on the ball by the club. Okay. Just reading that, lots of numbers. It's a mouthful. It doesn't look like it's so easy, but let's look what we need, look what we know, and use our equations. All right. So we're looking for force. We know delta T is 0.0020 seconds. We know the mass is 55 grams. We know initial velocity is 0. We know final velocity is 2 times 10 to the 2. Looking at impulse, we know that the change in momentum equals force times delta T. We're solving for force. So we're going to have force equals delta P over delta T. Delta P is just the change in momentum. So that's just P2 minus P1 over delta T. We know that P equals mv at the speeds that we're looking at and when things have mass. So we have m2 v2 minus m1 v1 over delta T. We're going to plug in what we know, and we end up with force equals 1676.83, or force is 1.68 times 10. Oh, is that a 3? I think that's a 3. Yes, that's a 3. Sorry, that's terrible. All right, there wasn't an A and B to that problem. So let's look at number 7. 7 says an object has a kinetic energy of 275 joules and a momentum of magnitude 25.0 kilograms times meters over second. Find A its speed. So we're looking for V. We know kinetic energy equals 275. We know momentum equals 25. Let's look at equations that we know. We know our equations of kinetic energy equals 1/2 mv squared. We know that P equals mv. So we're gonna rearrange P equals mv for M equals P over V. We could also solve for V, which we do in B. We're going to shove this into here, and we end up with kinetic energy equals 1/2 PV. Solving for V, we get 2 KE over P. We are given KE and P. We end up with 22.0 meters per second. All right, now B, we're looking for the mass of the object. We know that P equals mv. We're going to rearrange for V now because we're not looking for V, we're looking for M. So we're going to say V equals P over M. We're going to shove that in for V, and we get kinetic energy equals 1/2 M times P squared over M squared, or P squared over 2M. I don't know if we will get too much into it, but kinetic energy equals P squared over 2M. In undergraduate physics classes and graduate physics classes, that's something that you see every single day over and over again. We are going to solve for M. We're going to plug in what we know. and we end up with 1.1367, or mass equals 1.14 kilograms. All right, set 14. I know I'm going through this really, really quickly. If any of this is unclear, please send me an email and ask for more detailed instruction if you need it. All right, chapter 6, 26. Guy in a boat. Guy in a boat. Right? Yeah, this is a boat problem. All right, a 75 kilogram fisherman in a 125 kilogram boat throws a package of M equals 15 kilogram horizontally towards the right with a speed of 4.5 meters per second. I drew a little picture up here, neglecting water resistance and assuming the boat is at rest before the package is thrown. Find the velocity of the boat after the package is thrown. Again, these are all conservative forces. So we know that our initial kinetic energy plus potential energy is going to equal our ending kinetic energy plus our potential energy. So we're going to write down what we know. We know all of our masses. We know that our initial velocity is 0. We know that our final velocity of the package is 4.5. So plugging in everything that we are given, and we're going to solve for, what are we solving for? We're solving for the velocity of the man in the boat, which I've written here as VF squared. So we're going to plug in our values. We're going to get VF by itself, and we end up with 1/2 MP VF VP squared times -2 over MF plus MP. Plugging in everything that we know, we're going to get VF squared equals 1.51875. Taking the square root, we get the final velocity is 1.2 meters per squared. Now, kind of thinking about this problem, I'm sure that you've heard, I don't know that I read in the book that you necessarily talked about this, but it's very known kind of in natural American vernacular that every action has an equal and opposite reaction. So in thinking of this problem, you might be thinking that, you know, the man and the boat are really heavy and I'm going to throw something out of the boat, nothing's going to happen. Well, you're doing an action, you are giving something a velocity, there's going to be an equal and opposite reaction. Now, you're really, really heavy, and so that reaction is not going to be a large velocity, but you are going to get a velocity because you are pushing. You're going to be pushed back. All right, number 40. This is a fun question. I get to use different colors. Oh, look at the little astronaut question. That looks like a cute question. 42 shuffleboard discs of equal mass, one orange and the other green, are, oh, I drew blue. What's I doing? Are involved in a perfectly elastic glancing collision. The green disc is initially at rest and is struck by the orange disc, moving initially to the right at 5 meters per second. After the collision, the orange disc moves in a direction that makes an angle of 37 degrees with the horizontal axis, while the green disc makes an angle of 53 degrees with the axis. Determine the speed of each disc after the collision. Whew. These problems, I solved probably 1,000 of problems somewhat similar to these, a little more complex when I was studying for the PhD qualifying exam. Hundreds of these problems I solved probably. All right, so what we're given, what are we looking for? So we are looking for the speed of each disc after the collision. So we are looking for the VFs. We are given the initial velocities. The orange is 5 meters per second, and the blue, green in the problem, I screwed up, is 0. We are given theta 1 and theta 2, 37, 53. We're going to draw our triangles, and we're going to come up with the final velocity of blue times cosine 53 equals the x component of the final velocity of blue. Final velocity of blue sine 53 equals the y component of the velocity of the blue. We're going to do the same thing for the orange. We're just going to insert 37 instead of 53. We're going to use conservation of momentum. Now we could use conservation of energy. We could use lots of things, but we're looking at what we know. We're looking at really what is the easiest way to solve something. So we're going to use conservation of momentum. We're going to look both in the y and the x components. So starting with y, because y is kind of the simplest. Our initial p in y is going to be equal 0. Blue's not moving, and the orange is moving along the x-axis. Also, we know P equals MV. So we end up with this is a mouthful to say, the momentum, the final momentum in the y direction of the orange equals the negative momentum, final momentum of the blue in the y coordinate. So we're going to just insert what we know, and we're going to solve for the final velocity of blue, because that's one of the things that we're looking to know. And we end up with VBF equals VOF sine 37 over sine 53. Now let's look in the x-axis. We are going to have PIO plus PIB. PIB is going to zero out because our blue disk wasn't moving, equals our final momentums. We are going to, again, plug in what we know. We are going to cross off m's because these are of equal mass. The masses cancel out. And we end up with 5 times the final velocity of the orange, the cosine 37, plus the final velocity of orange, sine 37 cosine 53 over sine 53. Plug in our values, we end up with the final velocity of the orange equals 3.99 meters per second. I see foolishly that I did not end up going back and plugging this in here and solving for the blue, which I should have done. Do I have a calculator here? I do. Let me just solve for that super quick. Sorry. I'm not feeling well at all. Skipping steps here. You end up with 6.49 meters per second. Because these are moving in opposite directions, you could give one of them a, oh, the final velocities aren't moving in separate directions, sorry. They're both moving in the positive direction here. It's just your y is going to be negative. All right, 43. Moving right along. Another car one. This one I actually initially did incorrectly because I assumed that after the collision, the car and truck would be stuck together, which is a very common problem. Oh, sorry, I skipped 44. 43. Bullet problem. These are also super common in classic mechanics textbooks. All right, we've got a 12-gram bullet fired horizontally into a 100-gram wooden block that's initially at rest on a frictionless horizontal surface connected to a spring with a spring constant of 150 N/M. The bullet becomes embedded in the block. If the bullet block system compresses the spring by a maximum of 80 centimeters, what is the speed of the bullet at impact with the block? Okay, so our using conservation of momentum, because we've got frictionless surface, we are going to say that our initial momentums equal our final momentums, but because the bullet becomes part of the wooden block, our momentums end up being combined in the same. So using conservation of momentum, we end up with the mass of the bullet times velocity of the bullet equals the two masses together times their velocity. Rearranging to solve for velocity, we unfortunately have two unknowns. We don't have two equations, so we need to get another equation in order to solve for BB. We can also use conservation of energy. So let's do that to solve for our V, our final V, because we're looking for the speed of the bullet. And we get our initial kinetic energy and our initial potential energy are 0 for our bullet. And we get 1/2 big M plus little m v2 squared minus 1/2 kx squared equals 0, because our initial kinetic energy and potential energies are 0. Solving, plugging in, moving things around, we get VB squared equals 0.8 divided by 0.012 times the square root of 150 times 0.112, and we end up with 273 meters per second. All right, now onto the car problems. Like I said, I initially did this problem wrong. I did not read the problem all the way through. I looked at the picture and started to solve the problem and then went back, and it's asking for the velocity of the truck right after the collision. Well, if they're stuck together, it's going to be 18 meters per second. So clearly they're not stuck together. So we have a 1,200 kilogram car traveling at a speed of 25 meters per second, crashing into a 9,000 kilogram truck, also moving on what we would say is the horizontal axis or the x-axis, with a v equals 20 meters per second. The velocity of the car right after the collision is 18.0 meters per second. So we're looking for the final velocity of the truck. We know the final velocity of the car. We know the mass of both. We know the initial velocities of both. Using conservation of momentum, because there's nothing in here that's friction, air resistance, we're going to neglect those and say everything is let's say kosher. And we've got MC times VCI plus MT VTI, because P equals MV, equals MC VFC plus MT VTF. Plugging in what we know, because we have almost all of these values other than the final velocity of the truck, and we get 20.93 meters per second. That is wrong. It should be 20.9 meters per second. My apologies. All right, B. How much mechanical energy is lost in the collision? Count for this loss in energy. All right, so change in E is going to be the change in kinetic energy. We don't believe that there's any kind of spring action here. We're looking in the x direction, so there's no gravity. So potential energy is not something that we're looking at. So we're going to take the final kinetic energy, which is 1/2 MC BFC squared minus 1/2 MT BFT squared plus 1/2 MC BIC squared plus 1/2 MT BIF squared We solve for VT above. We were given the other above. We're going to plug in everything we know. And the change in energy is going to be 8636.3 joules, which we should write as 8.64 times 10 to the 3 joules, which I didn't do. My apologies. And it's negative because there's a loss. All right, so that was 44. That is everything for last week. Again, please reach out if this was unclear. I realized that I just went very quickly through everything and didn't solve the problem. For me, watching somebody solve problems is better than just looking at what someone has already done and kind of watching them circle things. So please reach out if any of this is unclear, you need additional help. Next week, hopefully I will be feeling better, and then I will go back to my incredibly long, incredibly stupid dad joke, annoying videos that I hope you're at least learning something from. All right, guys, thank you so much.